Bohr's model was very effective at describing electrons as particles and arranging them into rings around the nucleus. But that doesn't take into account the fact that electrons behave both like particles and like waves. In order to do that, we have to look towards quantum mechanics. We start with the Heisenberg uncertainty principle, which tells us that we cannot simultaneously know both the position and the velocity of an electron. The more we know about one, the less we know about the other. This leads us away from talking about finite locations of electrons and more at looking at areas where we have a high probability of finding electrons. And so we get into Schrodinger's wave equation, which gives a treatment mathematically of both the wave and particle nature of matter. And the solutions to Schrodinger's wave equation give us these probability densities, and we call this quantum mechanics. So you'll notice in this picture here on the right that there are a high concentration of blue dots here towards the middle and fewer as we move outward. And so this is a probability density. Technically, all of our pictures of atoms should have fuzzy edges because they're probability densities. But we tend to draw them with finite edges because it's easier to draw. First thing we have to do to look at quantum is to divide each energy level into subshells or sublevels. Each energy level consists of n subshells, where n is the number of the energy level. So the first energy level has one subshell, it's an s subshell. The second energy level has two subshells, an s subshell and a p subshell. The third energy level has three subshells, an S, a P, and a D subshell. The fourth energy level has four subshells, S, P, D, and F, and so on. Now, each of those subshells is divided further into orbitals. Sometimes one, typically more than one. So we got to look at what an orbital is. An orbital is the region with the highest probability of finding an electron given a certain set of energies and natures of the electron movement. The solution to Schrodinger's wave equation gives us the shape of the orbitals. If you want to get into that, you got to go take some multivariable calculus. We're not going to do that here. We're just going to look at the shapes that we get out of it. You'll also need to know that each orbital can hold only 2 electrons, and we'll look at exactly why that is in a few minutes. So we have s orbitals. That was the first type that we looked at. S subshells. In each s subshell, there is a single s orbital. It's spherical in shape, and the size of the sphere increases as n increases. It's important to recognize that the probabilities are more on the outer edges of this sphere, and they're not continuous all the way through the center of the sphere. By which I mean you don't have a high probability of finding an electron in the nucleus at the center of the sphere. Next, we have p orbitals. In each p subshell, there are 3 p orbitals, starting in energy level 2. They have 2 lobes with a node between them. You'll notice in this picture, the lobes have fuzzy edges because they're probability densities. We tend to draw them with defined edges as a dumbbell. Next, we have d orbitals. In each d subshell, there are 5 d orbitals, starting with the 3rd energy level where we first see the d orbitals. 4 of them have 4 lobes apiece, and the 5th one, the dz squared, looks like a p orbital and then has a donut around the middle. Next, we have the s subshell. Now, if you notice the pattern, there was a single s orbital, there are 3 possible p orbitals, there are 5 d orbitals, and so, in keeping with the odd numbers, there are 7 possible f orbitals in each energy level, starting with the 4th. These shapes are really fun, and no, you don't have to know them. You don't even really have to know the shapes of the d orbitals a whole lot. And as I said, each of these orbitals can hold 2 electrons. So that would mean that in the s subshell, we can put 2 electrons. In the p subshell, since the p subshell consists of 3 orbitals, we can put 6 electrons, and so on. Let's look at why we can only put 2 electrons, though. is a property called the Pauli exclusion principle. The Pauli exclusion principle says that an orbital may describe two electrons that have opposite spins. Basically, we have a series of numbers that quantify the properties of the electrons. The last number that we have is the spin, which is either, as we describe it, clockwise or anti-clockwise, or spin up and spin down. Because there are only two possible spins, we can only put two electrons in each orbital. And so, as I was saying, that leads us to this idea that the three p orbitals can hold a total of 6 electrons, 2 apiece. The set of d orbitals can hold 10 electrons, since there are 5 d orbitals, and the set of f orbitals can hold 14 electrons. The interesting thing is, this is related to the structure of the periodic table. You'll notice that on the far left-hand side of the periodic table, there are 2 columns together. These correspond to the s orbitals, where we can put 2 electrons in the s block. For the p orbitals, we can put a total of 6 electrons into the p orbitals for each energy level. So this p block is 6 columns wide. Similarly, the d block is 10 columns wide, and the f block is 14 columns wide. So what do we actually do with this? Let's start actually drawing atoms. We'll start with hydrogen. Hydrogen has 1 electron, because it only has 1 proton. And if we look at where it is on the periodic table, it's up here. That's in the s block, and it's in the first energy level. So we have our nucleus there in the middle. We put our 1s orbital. We put 1 electron on it. Now, it'd be really annoying if we had to draw this picture every time we wanted to indicate the configuration of hydrogen, and especially more annoying as we get to more and more electrons. There's another way to write electron configurations, and we're going to do both. The way that we write electron configurations is with both a number, a letter, and then a second number as a subscript. So this shows the distribution of the electrons in the atoms. So we have a number that tells us the energy level. We have a letter that tells us what type of orbital it is, and we have a superscript number telling us how many electrons are in that orbital. So we're going to do this as we go along for each one. So for hydrogen, we had 1 energy level, the s orbital, and there was 1 electron in it. So our electron configuration is 1s1. Let's look at helium next. Now we have 2 electrons. Helium is over here, but still technically in the s block. So we'll start with our hydrogen picture. All we have to do to get from hydrogen to helium is add another electron, and we're still in the s orbital. We haven't filled it up yet because it can hold 2 electrons, so we just put another dot on that ring. And that electron configuration now is 1s2, because there are 2 electrons in the 1s orbital. All right, let's continue. Let's look at lithium. Now it has 3 electrons. Lithium is over here. You'll notice that it's in the 2s, so we filled up 1s, now we go on to 2s. So in order to depict the 2s, we put another ring. And we have 1 electron left to place, so we put a dot on that second ring. Our electron configuration now is 1s2, 2s1. Okay, I'm going to skip beryllium because that I think is a natural extension. We put another electron in that second ring, and then we change it to 1s2, 2s2. I want to go on to boron next. Now, boron is one of the ones on the activity that you picked up on your way in, so you might want to get that out and start drawing as well. So for boron, that's here. Notice that we're into the 2p section. There is no 1p, because the first energy level has only 1 subshell. So we've filled up 1s, we've filled up 2s, now we've got to go on to 2p. Now, if you recall, there are 3 different p orbitals. There's px, py, and we depict pz at an angle. When we draw these all together, it gets really